Bitcoin as a state transition system. The state transition function can be defined roughly as follows. For each input in a transaction, if the referenced UTXO is not in the initial state, return an error. If the provided signature does not match the owner of the UTXO, return an error. If the sum of the denominations of all input UTXO is less than the sum of the denominations of all output UTXO, return an error. Return a new state with all input UTXO removed and all output UTXO added. Mining. Because Bitcoin is trying to establish a decentralized currency system, it's necessary to establish a method that combines the state transition system with a consensus protocol that allows anyone to agree on the order of transactions. This protocol allows the network to have strict control over the ownership of the currency at any time. The network is intended to produce roughly one block every 10 minutes, with each block containing a timestamp, a nonce, a reference to, a hash of, the previous block and a list of all the transactions that have taken place since the previous block. Over time, this creates a persistent, ever-growing blockchain that constantly updates to represent the latest state of the Bitcoin ledger. The algorithm for checking if a block is valid, expressed in this paradigm, is as follows. Check if the previous block referenced by the block exists and is valid. Check that the timestamp of the block is greater than that of the previous block and less than 2 hours into the future. Check that the proof of work on the block is valid. Let S0 be the state at the end of the previous block. Apply the state transition function for all transactions contained in the block and transactions. If any application returns an error, exit and return false. Return true, and register SN as the state at the end of this block. Note: the block does not contain the status. This is just a concept that the nodes consider when validating a block. The validity condition in the above list is the requirement for proof of work. The precise condition is that the hash of every block resulting from applying the SHA-256 function must be less than a dynamically adjusted target. The purpose of this is to make block creation computationally hard, thereby preventing attackers from remaking the entire blockchain in their favor. Because SHA-256 is designed to be a completely unpredictable pseudo-random function, the only way to create a valid block is simply trial and error, repeatedly incrementing the nonce and seeing if the new hash matches. In order to compensate miners for this computational work, the miner of every block is entitled to include a transaction giving themselves 12.5 BTC out of nowhere. Additionally, if any transaction has a higher total denomination in its inputs than in its outputs, the difference also goes to the miner as a transaction fee. The rewards given to the miners allow the network to work optimally, and at the same time it is the only mechanism to put new coins into circulation. Merkle trees. An important feature of Bitcoin is that the block is stored in a multi-level data structure. The hash of a block is only the hash of the block header, a piece of data that contains the timestamp, nonce, previous block hash and the root hash of a data structure called the Merkle tree storing all transactions in the block. A Merkle tree is a type of binary tree, composed of a set of nodes with many leaf nodes at the bottom of the tree containing the underlying data, a set of intermediate nodes where each node is the hash of its two children, and finally a single root node, also formed from the hash of its two children, representing the top of the tree. This data structure allows that if an attacker tries to modify any of the transactions, which implies changing the hash, the error will spread to the hash of the head block. Consequently, the block will be rejected because it will no longer comply with the proof of work. A Merkle tree also is important for system sustainability. A complete node that processes an entire block takes up about 15 gigabytes. Merkle tree allows a protocol known as Simplified Payment Verification (SPV), that supports light nodes, which download the block headers, verify the proof of work on the block headers, and then download only the branches associated with transactions that are relevant to them. This allows you to safely verify a transaction without having to dispose of 15 gigabytes of disk space. On the left, you can see one of the branches of a Merkle tree validating a transaction. On the right, if you try to make a change in a transaction, the error will spread up the chain, invalidating it.